Hello, so today I have to discuss about two problems that appeared in CMI 2021 entrance exam. So the first question is about on limits and the second question is about a bit of inverse trigonometric functions and a bit of definite integral. So the first question says fx equal to x by x plus sin x and gx equal to x to the power 4 plus x to the power 6 by e power x minus 1 minus x squared. Now I have to check limit x tends to 0 and x tends to infinity behavior of both f and g. For the next question, I have given f to be tan inverse function. G is defined to be g of v equal to definite integral from 0 to v f t dt. Then I have to check some values of f and whether g is increasing or not, whether g is odd or not. So let's get started.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
For the first question, fx equal to x by x plus sin x. And limit x tends to 0, fx is just what? Limit x tends to 0. X by x plus sin x is just limit x tends to 0. 1 by 1 plus sin x by x. You know that sin x by x goes to 1 as x tends to 0. So this limit is just 1 by 1 plus 1, that is half. Similarly, limit x tends to infinity, x by x plus sin x. This is same as 1 by 1 plus limit x tends to infinity sin x by x by same procedure. And sin x by x goes to 0 as x tends to infinity because it is sandwiched between minus 1 by x and plus 1 by x, and both these bounds goes to 0 as x tends to infinity. So this goes to 0, so this limit is just 1. So x tends to 0, fx is half, okay, true. It doesn't exist for x tends to infinity, this is false. I have to check x tends to infinity and 0 for both g. Now g of x equal to x power 4 plus x power 6 by e power x minus 1 minus x squared. Now limit x tends to 0, gx equal to limit x tends to 0, this thing. Now we have one important thing, that limit x tends to 0, e power x by 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus x to the power 4 by 4 factorial, this thing is 1. You can show that. So I can replace e to the power x by this expression in this limit. So calculate it in this way. X power 4 plus x power 6 by e power x minus 1 minus x squared. So 1 is cancelled out, x squared 1 half is cancelled out. So this is x minus x squared by 2 plus x cubed by 6 plus x to the power 4 by 24. And you can just cancel one power. So this is just limit x tends to 0, x cubed plus x power 5 by 1 minus x by 2 plus x squared by 6 plus x cubed by 24. And you see that x tends to 0, this goes to 0, this part also goes to 0. So this goes to 0 by 1, that is 0. And what about limit of g when x tends to infinity? Remember one thing that is very important. For all polynomials, like for any polynomial p of x, as x tends to plus minus infinity, x tends to infinity, px by e power x, this always goes to 0. Like we can think it in this way, the growth of the exponential function e to the power x is so large that so large as compared to polynomials that this ratio goes to 0. Like if you keep increasing x, e power x increases so fast that the ratio px by e power x is almost 0. Like it's so small. You can think in it this way, like exponential functions grow much faster than polynomial functions. To prove that, you can use induction on the degree of polynomials, or you can just use L'Hospital's rules repeatedly. I'll read this as an exercise. This is very well known. Now using this, now think this in this limit. How does this limit look like? The denominator is dominated by an exponential function. It is equivalent to an exponential, and the numerator is equivalent to a polynomial. So this ratio, this also goes to 0, like it becomes very small. Because you can divide this by x power 6, so this becomes 1 by x squared plus 1 by e power x by x power 6 minus 1 by x power 6 minus 1 by x power 4. As x tends to infinity, this goes to 0, this part goes to 0, and as x power 6 by e power x goes to 0, so this goes to plus infinity. So this maintains, and by 1 by infinity, that is 1 by infinity from is just 0. So this ratio just goes to 0. You can easily check that out. So x tends to infinity, gx is finite, that is true. X tends to 0, gx is 720, this is false. So this question is done. Let's move to the next question. F of 1 is pi by 4, it is obvious because tan inverse 1 is pi by 4, because tan pi by 4 is 1. This is true. The second part, f1 plus f2 plus f3 equal to y, you can easily verify this in this using this thing. Tan inverse x plus tan inverse y plus tan inverse z equal to tan inverse x plus y plus z minus xyz by 1 minus xy minus yz minus zx. So you can put x equal to 1, y equal to 2. What were my numbers? Yeah, 1, 2, 3. And z equal to 3. So you can see that x plus y plus z minus xyz is just 0 in that case. Both are 6 minus 6, 0. So in that case, this quantity becomes like f1 plus f2 plus f3 becomes just tan inverse 0. And you can think it as pi. Like, how does the graph of tan inverse x look like? So f of 1 plus f of 2 plus f of 3, it just almost goes like, if you add them, just move this on top of this, then move this on top of this, it's almost like pi. So this is true. Okay, but this is for principal values. So like if your main thing goes much more than that, you have to adjust by plus minus pi's. You can find this in any book of inverse trigonometric functions. This is true. I have to check whether g is even or odd and g is increasing or not. So I have g of x equal to integral 0 to x tan inverse u du. As g dash x by fundamental theorem of calculus FTC, because tan inverse is continuous, g dash x is just tan inverse x, and tan inverse x looks like this thing. It is greater than 0 for all x greater than 0. Like for x less than 0, g dash x less than 0. So if g of x was strictly increasing on whole real line, so it would mean that g is strictly increasing on R would imply g dash x would be strictly greater than 0 at least. But here, like in this case, g changes sign. Like for x less than 0, dz x strictly less than 0, and for x greater than 0, dz x is strictly greater than 0. So this statement is false. And for the g is an odd function or not, you can just use a simple substitution. I have g of x equal to integral 0 to x and inverse u du. To check g of minus x is just this thing, integral 0 to minus x. So write it more neatly. And inverse u du, we just substitute u equal to minus v. So it just becomes integral from 0 to v tan inverse minus v and d of minus dv. So minus dv. And tan inverse of minus v just minus tan inverse of v. So this is just becomes plus. So it becomes 0 to v tan inverse v dv. And that is same as g of sorry, this is not v, these are just 0 to x. So this is just gx. So g is an even function. So this is not odd. You can also have an important thing that if a derivative of a function is even, then the main function is odd, and the vice versa. If the derivative is odd, main function is even. As my g's derivative was tan inverse function and tan inverse is odd, so g must be even. You can also conclude it directly in this way. So this is also false. So my first two statements are true and last two statements are false. And we are done. This ends the solution.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.